Good afternoon, and I'd like to welcome everybody to this doctoral thesis defense, and of course a special welcome to the doctoral candidate, Professor Jesper Hattel. A special welcome to Professor Jesper Hattel. It's always nice to have an experienced dean and chairman of the proceedings in the background. I'd also like to add a special welcome to the two official opponents, Professor Michel Bellet from MIN Paris, which is now one of the 11 institutions that has formed the Université Paris Sciences et Lettres. And Professor Paulo Martins from Instituto Superior Técnico at the University of Lisbon. And also a welcome to Professor Christian Hjortsson from the Department of Civil and Mechanical Engineering at this university, who is the chairman of the assessment committee. My name is Rasmus Larsen. I'm the university provost, and I'll be the chairman of these proceedings. And I'll just say a little bit about the proceeding and what has gone before we have reached this stage. So Jesper Hattel's doctoral thesis is entitled Multiphysics Modeling of Manufacturing Processes, and it was handed in to the university on December 20th, 2023. And after the assessment committee's positive assessment of the thesis dating August 29th this year, the thesis was accepted for defense by the Academic Council on their meeting on September 17th. And this is the defense that we'll have today. So after my small introduction here, I'll give the word to Jesper Hattel, and he'll present his work in a lecture of approximately half an hour's length. And thereafter, I'll give the word to the official opponents, who will discuss the thesis and its content with the candidate. After the official opponents, there's also the opportunity to ask questions ex auditorio, and if you have prepared such a question, if you think of such a question during the lecture, please register with me immediately after the lecture. We'll have a small break there, so there is time to come forward. And after that small break, we'll reconvene in the auditorium, and the official opponents will lead the discussion with the candidate. I shall inform everybody that the proceedings are being recorded, both for documentation, but also for the benefit of those who have not been able to be present today or to watch the streaming of the event. After the questions, the formal part of the defense is over. The assessment committee will adjourn and finalize their final recommendation to the university on awarding the degree. After the formal event here, the university will host a small reception in the lobby outside the auditorium here, and you're all welcome to join. And with that, I'd like to end my introduction and give the word to Professor Jesper Hattel for a lecture on his thesis, Multiphysics Modeling of Manufacturing Processes.
So, Thank you very much for this kind introduction. Imagine that it was actually 31 and a half years ago that I stood here and defended my PhD thesis in the same room, but with plastic overheads. So something has happened since then. So today, the title of my thesis is Multiphysics Modeling of Manufacturing Processes. And you might ask, what is manufacturing? Well, it comes from Latin, the manufactur, which means made by hand. But today, you could say that many manufacturing processes, they're highly automated and carried out by machines in close connection with computers. So one could argue that it should be rephrased into made by machine and to a large degree controlled by a computer. So if we look at the overall manufacturing chain, we have the materials coming in to the left, we have the factory or the plant, and then we have our final products. That's actually the overall value chain. In the factory, we have a series and chain of manufacturing processes composed of single process steps. And what we're frequently interested in is the correlations between what we can control, the process parameters, what we can measure, the process signature, and the final product quality. So it's all about getting those correlations to get the right products. But it's not really only the correlation, it's also the causation. And for sure, there is a difference. And this is, you could say, illustrated by this very nice figure. What you see here is there is a correlation between the worldwide non-commercial space launches that correlate with the amount of sociology doctorates awarded in the US. So when one goes up, the other one goes up. When one goes down, the other one goes down. So there is a correlation. So it could be tempting to say, okay, well, if we want more PhDs in sociology in the US, we just need Elon Musk to send more non-commercial rockets into space. That would be utter nonsense, because there is no causation. So the real aim is actually causation, but based on the knowledge of the correlation. So we revisit this figure again, and then it's all about getting the right product quality and then finding out how to adjust the process parameters, select the material, and so forth and so on. And there we need to use well-planned experiments, proper statistical methods, and multiphysics-based models. And this is what I'm doing in order to distinguish the correlation and the causation. So mathematically, this is actually, in fact, an inverse problem. So what you see here is that the production goes from left to right. You have the raw material coming in, you have the production, and then you have your final product. But the design process goes from left to right, because you know what the product is actually. Let's do it here. Is it able to point? Yes. We know what the end goal is, but we don't know how to make it. So when you design something, you know what it's supposed to do, but the inverse problem is to select the materials, the processes, as well as design the production equipment so that the end solution is satisfied. And that is mathematically an inverse problem, and that's what makes it difficult. So what is multiphysics? That was manufacturing, now it's multiphysics. Well, it's numerous physical phenomena often taking place simultaneously in a coupled manner. So what you see here are some well-known examples of relevant physics. You see here fluid flow with three surfaces. You see phase changes from a glass of water actually freezing, and then you see thermally induced stresses and deformations. And all these are not related to manufacturing per se, but they are phenomena that will often take place during manufacturing and often together. So how do we solve this and model this mathematically? Well, we use partial differential equations. Partial differential equations are based on conservation principles, that is, in essence, balances together with descriptions of materials. So we have heat transfer conservation of energy, we have fluid flow conservation of mass momentum energy in solid mechanics, that's simple force equilibrium. So these are the considered manufacturing processes in my work. Metal casting, you see the mill being put down. You see this big ship propeller here with a car below it. It's humongously big. Then you have spray forming with some products below it, and friction stir welding, a mechanical process, quite interesting, and some of examples of the products below it. Then we have tape casting, that's used for tapes used in the electronics industry. We have pultrusion, you have some products below there, some profiles, and then you have additive manufacturing, also known as 3D printing, with some examples below there. So how do we go about modeling this? Well, we use analytical and numerical methods. So you start out with the partial differential equations. That's what we have here, and plus a lot more. And then you have analytical solutions at paper and pencil. You get some formula, you get some curves, and then you can actually derive whether it works according to how it's supposed to work. We also do numerical methods. This is what this is about. And there you type it, or you could say program it into a computer. You get numbers and lots of numbers. That's why it's called numerical. And then you get curves and plots as well. But they are much more general than the analytical ones. So what are we doing when we make a numerical solution? Well, we divide our domain into different cells and elements. And this is what you see here, some examples of cells and elements. And in essence, when we solve these partial differential equations, what we do is that we establish the physical balances on the small volumes. Physical balance, heat conservation, momentum conservation, force equilibrium. That's in essence what we do, and then we get tons and tons of equations that we solve, and then we can get the curves and color plots and blah, blah, blah. Something we always have to do is verification and validation. Now, in verification, we ask the question, are the equations solved right? And the only way we can test that is to compare with a well-known analytical solution. This is actually an analytical solution from one of my courses in heat transfer. Some of you would recognize that. So we check for mathematical consistency by comparing with an analytical solution to a known problem. Then in the validation, this is the real test of the numerical method, because here we flip the question and ask, are the right equations solved, instead of are the equations solved right? And the only way, then we test, is the model a good representation of our physical system, and the only way we can find that out is to compare with experiments. This is just an example of experiments here. So this thesis consists of 34 scientific publications out of more than 300 publications that I've been involved in, and I have chosen these 34 to write a coherent story, and I hope the evaluation committee thinks that this is pretty coherent. And these are the 34 papers that you see here with their front pages: metal casting, spray forming, friction stir welding, tape casting, pultrusion, and additive manufacturing. So the first two papers was a steel forging ram. It was a steel forging ram that had centerline porosities as well as segregation. And we did a simulation in Magmasoft to analyze this, and this is what you see here: the fluid flow, the mold filling, the solidification, and that was actually a simplified model as compared to the physics really taking place here. We could predict the centerline porosities. We could also, to some extent, predict the segregation. And then we used this kind of simplified model. People would know that solving Navier-Stokes equations is for sure not simplified, but this was at a scale where these phenomena normally not take place. So it was actually simplified. And then we did a multi-optimization objective optimization problem where we wanted to get rid of those centerline porosities, but also make it more energy efficient. So we found the optimized layout. The weight of the molded material went from 60 tons to 46 tons. It was a success. It was test cast, and it showed no defects. And this was actually obtained by this relatively simple model, calculating many scenarios, and then we could optimize and ask the computer, please give us a layout that gets rid of the defects. The next two papers was about ductile cast iron, improved micromechanical models that could somehow address the nonlinear behavior already in the elastic regime. So here you see some examples of ductile cast iron. Now, the microstructure in ductile cast iron contains soft graphite nodules, and these are for castability. But typically, you don't assume that they can carry any load because they're soft. So therefore, you just assume that there are holes when you dimension the thing. But the point is that during manufacturing, what happens there? Because you have different thermal coefficients, expansion coefficients of the nodules and the surrounding matrix, which means that you get localized residual stresses. And this is important for how it carries afterwards. So people would normally look at those as homogeneous isotropic elastic bodies, but there was absolutely no consensus in literature as to how to model the Young's modulus. You see it goes from 0 to a lot, and that's a big variation, I would say. So what we did was that we looked into literature and had a look at those nodules. We found out they're not isotropic, but composed of conical sectors made of platelets. And then we proposed several divisions into conical sectors. And then we did a unit cell approach. This was our first model. And then we could do something like this, where you have elastic and plastic deformation in a unit cell approach. And then we could predict some macroscopic nominal values for Young's modulus and Poisson ratio. And it was still 15 to 20% off. So we were on the right path. Sorry. Making a more advanced model where we did a simulation, a macroscopic casting simulation in MagmaSoft, so we got the cooling history. That's very important for the residual stresses. And then we imported the real structure from the test specimen. We had this loading history there, and then we did a cross-section loading simulation in Abacus. And with that, we got a much more realistic description. So you can see here, if I can get it to work. Can I try here? No. I don't know why it doesn't work with the... Okay, anyways, but you can see the figure to the left, the two reddish ones, they are around 3–4% from the experimental values, and this was with the advanced model. And what was really interesting here was that we could then provide the first theoretical explanation for the nonlinear behavior already in the elastic regime for this material. So you needed to look in the micro mechanical behavior of the material to say something about its behavior macroscopically when loaded in real life. So the next process was spray forming. Now, spray forming is a process where you have a melt, it's atomized, you get a lot of droplets, and then you build a billet. Now, when we made these models, there were only single droplet models in literature. So what we proposed was a one-dimensional model. You see that here. And then we turn it around, and then you see that it was a balance between the droplets and the enveloping gas, where we solved the one-dimensional momentum equation as well as the energy equation for the droplets. This is what you see here. And with this, we could predict the temperature during flight, solid fraction over distance, as well as compare with experiments from secondary dendrite arm spacing. So this model was just the atomization model. This we wanted to couple with the building of the substrate, and this is what you see here, solving the standard heat conduction equation, and then also taking into account the droplet distribution along the axis as well as along the radius. And this is what you see here. And we needed to account for shading with various geometrical considerations as well. That was rather involved at the time. And then we had this coupling between atomization and deposition. You see some results here. Building a Gaussian bill. This is where you have the atomization point right above where you built. Then you just get a Gaussian bill due to the distribution. But if you want to make billets where you have shooting from an inclined, you could say, position, then you get a billet like this, and this is what you see here. This was a growth of cylindrical billet, and here we needed to take the shading effect into account. Then we finally, in spray forming, did a model in open foam, which was a more, you could say, advanced CFD program, where we looked at the calculation domain relatively close to the nozzle positions and looked at both primary and secondary breakup. And then we could make a simulation like this, taking turbulence with a K-epsilon model into account. And then this was a substantial improvement as compared to the literature at the time. Now we come to friction stir welding. That was this process where you have a rotating tool. It's a mechanical welding process, and then you weld the two parts together. And here you have an indication of the friction stir welding process. we did a very fundamental analysis of the heat generation at the surface of the tool and the shoulder. Nobody did that in literature before at the time. So we defined a state variable. It was 1 when there was sticking, because the interface condition is extremely important, 0 when there was sliding, and in between a combination of the two. And then we derived this analytical solution that was a unified model, and it actually contained all the known analytical solutions, special cases at the time. And this was kind of taking them all into account because it was a much more general formulation. It was experimentally validated, and that validation suggested a close to sticking condition. Then we did a CFD model. CFD, computational fluid dynamics, it's something with flow, right? And you might ask yourself, how can you make a CFD model for a solid yielding material? It's not flow. Well, it is flow in the sense that it's so soft that it flows. And we go about the basic relation between yield stress, strain rate, tensor, and viscosity. And then we also made a very much needed categorization of the different ways of prescribing the heat generation in friction stir welding. And here you see a simulation. You have the rotating tool, then you have the material coming to it. And then you see some tracer particles being swept around the rotating tool, and we can compare with experiments, and we found quite nice agreement. Then we went to thermomechanical models. This is a classical quasi-steady state thermomechanical model with a moving heat source. So this is quite standard in welding, you could say. But the trick here is actually to find the heat source, really to calibrate it. So with this, we could make parameter variations where we varied the welding velocity as well as the rotational velocity. We could look at temperature fields. This is what you see here. And we could also look at the longitudinal residual stresses as a function of the choice of these process parameters. Then we did a much more advanced model, a dynamic solid mechanical model with flow. This is what you see here, just at the very beginning of the friction stir welding. The very interesting thing about this model is that the interface condition between the material, between the tool and the matrix, is not prescribed. It's part of the solution itself, and that made it very special, this model. We could predict the so-called flow arm, and we could also predict a void there that could lead to some tunnel defects, and so forth and so on. These models are actually multiphysical. That means that they take a lot of calculation time. They are complex. So we tried and think, okay, can we make a simpler model? And then we suggested the thermal pseudo-mechanical model. And this way we bypassed the multiphysics, and instead of making an experiment so we knew the total heat generation, we tried to make it based on material information instead. So we made a model that where the temperature-dependent yield stress was controlling the heat generation. There is still some mechanical information in the model, but it's only a thermal model, which means that it calculates extremely fast. So we got almost the same calculation time as just prescribing the analytical heat source, but then we avoided temperatures over the solid temperature, of course, because then it switches itself off. And then we did some validation against experiments, and there was actually quite nice agreement. So in friction stir welding, we also looked on the effect of softening on residual stresses. This was the quasi-steady state mechanical model I showed before in Abacus. And we used a simple softening model by Mu and Grong. It's based on dissolution of hardening precipitates. So the red curve is when it heats up. The blue one is when it cools down. And here we have this example. And we had two cases, cold and hot welding conditions. And we were actually able to capture the well-known M shape from experiments that you actually see in literature. And of course, the softening was obviously taking more effect during the hot conditions. That is, of course, expected. So then I come to the next process, tape casting. Now, tape casting, this process here where you make very small tapes to be used in electronics industry, and This is the doctor blade region where it flows out, and this is where all the magic happens, you could say. What you're frequently interested in here is the thickness of the tape, because you want to control how thick it is, and that thickness you can actually calculate if you know the velocity field. Because if you know the velocity field, you can use the mass balance, the continuity equation, and then you can find the thickness. So what we did was that we suggested a steady-state velocity field solution for a power law fluid. In literature, at that point, it was only Newtonian fluid that was suggested. So we looked at a power law fluid, suggested this. But what we also did was that we augmented this. So it became a quasi-steady-state velocity field when the fluid height decreases. Because when the pressure height decreases, it will change the velocity field. So this we suggested as well, and that was really the novelty of that paper. And we could actually get very nice results as compared to experimental findings. We also looked at two doctor blades, because two doctor blades, this is actually where you better can control the height of the reservoir. And then we gave some contributions to the literature with the velocity field, also for a Bingham fluid. We also looked at the side flow. A lot of people in literature, they talk about the side flow. So when you have it flowing out of the tape caster, it flows a little to the sides. And then some formula were given in literature, but they were never derived. So we thought, okay, well, people were using these, but never told why. So we just made a small, you could say, analysis as to why it actually looked like this. And then we used a 3D CFD model in ANSYS Fluent to actually simulate the side flow. We compared against experiments for the side flow as a function of substrate velocity, doctor blade height, and initial slurry height. And we found very nice agreement. And we could also predict the initial trumpet shape. That, yeah. We know how that looks like. That's kind of a profile, right? But anyways, the initial trumpet shape, and that was the model versus experiment that you see here. And of course, it flows to the sides in the beginning very much because there is a free boundary very close. And then the final paper in tape casting was a simple drying model in 1D that it was emulated by the water ceramic system. So if you see here, the drying you have here with the blue heater, and the point is that it's one-sided drying at the surface. So it's a balance between the slow diffusion through the tape and the fast evaporation at the surface. And ideally, you would like to get a more or less constant concentration throughout the tape, and this is, of course, not possible. But you would like to at least get there to some extent. So we made a simple model for the heat conduction equation in 1D. This is what you see here, very simple. Then we got some temperatures. And then we also realized that the diffusion coefficient for the dry skin, it has a much lower diffusion coefficient than the wet material. Combining that, we could solve fixed section law, and then we could get the temperature profiles through the tape for fast, intermediate, and slow drying. Getting to the next process of pultrusion. Now, pultrusion is a very interesting process where you have fibers coming into a die, you add resin, and then you cure it, you kind of heat it, and then it hardens. And then out comes some profiles. So we started with a simple 2D rotational symmetrical model where we found the centerline temperature as a function of distance as well as the degree of cure. And the degree of cure, it's how hardened it has been. That has to be around 0.9 or higher. Then we continued with comparing some different solvers from literature, ADI, transient, implicit, steady state, and so forth and so on, to see what was the most efficient seen from a computational viewpoint. And then we did a small DOE where we looked at how fast can you actually pultrude a part if you want to make it as thick as possible, but pull as fast as possible. And pulling fast, of course, increases productivity. But if you pull fast, it doesn't have the sufficient time for curing. So, of course, these are conflicting objectives, and then we made this, you could say, optimization curve. Then we went to the very first in literature thermochemical mechanical model of pultrusion. Nobody ever did a thermochemical mechanical model of pultrusion before, so we took the model from before, and then we took a 2D plane strain cross-section moving through the die. And then we used the Cure hardening instantaneous linear elastic model, and then we got these results for the in-plane normal residual stresses. They are almost symmetrical. That's not surprising, because it's an almost symmetrical case. And these, we have tension in the center, compression at the surface, and that could actually lead to tensile cracks in the center. Then we continued and said, okay, well, this was a plane strain. A plane strain assumption means that you get longitudinal stresses that are very high because they're constrained. So we looked at a generalized plane strain as well as a 3D model. And that was augmented by this. This is what you see here. This was a plane strain. You get very large longitudinal stresses. So we looked at smaller but varying longitudinal stresses in generalized plane strain. And then we went to 3D. And here are smaller but more realistic longitudinal stresses with tension in the center. So if you want to look at not only in-plane stresses but also longitudinal stresses, the 3D model is probably preferable. These models were used for two industrial cases. The first one is this L profile. The problem with this L profile is that when it's pulled out of the die, it has spring in. So it does like this. So it deforms inwards. And we were able to predict that with our model. You see here it deforms a little inwards. And then when we compared with an experimental finding, we actually got very good results. Then there was another hollow profile that also suffered from inwards bending. You can see that there when they're put on each other. And then we were simulating that in a model. And this is only 1/4 of the model, but you see that it gives this inwards bending as well. So we could really use this thermochemical mechanical model for predicting final deformations. Then finally, in pultrusion, we did a 3D steady-state thermomechanical model. Now, these other models, they were transient. That means time-dependent. It means they are taking a lot of calculation time. So it's not difficult to make a transient nonsense, a steady-state model for solving the temperatures, but it's more difficult for making a steady-state model for solving stresses and strains as well. So we were inspired by some people also from welding who did this before, and then we were integrating deformation rates along streamlines to get final deformations. And this model here, it was actually showing the same accuracy as the 3D transient thermochemical mechanical model I showed before, but it was calculating much faster. So if you want this steady-state situation in pultrusion, and this is what you often want because it's a steady-state process, then you should definitely go for that. But if you have startup or stopping problems that you want to analyze, then of course a steady-state model is not sufficient. Then comes the final group of manufacturing processes, that's additive manufacturing, also known as 3D printing. In the beginning, we made a simplified model for optimizing the scanning strategy of a 3D printed rod. So this was a 3D printed rod. You see when you 3D print, you have a laser, you melt some material, and then you cut it from the base plate. Now this was scanned, typically classical scanning back and forth in squares or lines. So you scan, 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 and then you cut it, and how does it look then? It looks like this. It bends. So when it's cut from the base plate. So that is, of course, a problem. So we thought, okay, how could we actually scan in another way so that it didn't bend? So we sectioned this part in different levels. And the green levels there, we used the so-called local in-out spiral scanning strategy with the laser. We made a simplified thermal model, and then we compared that for the local in-out spiral with an advanced model in Abacus, and we saw quite good agreement. Not the same, but relatively good agreement. And then we could use that optimized solver to ask the computer, please tell us how to scan. Instead of just doing like this, so it bends, please tell us how to scan so it doesn't bend when it's cut off. And you see the one there below the bending one, that was the one with the optimized scanning path, and it was as flat as it was when it was not removed from the base plate. And that was because we could optimize. Not surprisingly, the optimized scanning path was scan a little here, scan a little here, scan a little there, which is called island scanning, because then they can just subtract independently instead of one long rod that subtracts like this and then does like this. So that it was not a surprising result, but it was even so a very interesting result. But this called for a lot of dedicated experiments. So it's not a general procedure, you could say. You could say that we substituted some of the complex partial differential equations with empirical knowledge that we put into our reduced order model, which means that it starts getting problem dependent. We could probably not have done that for a very advanced 3D geometry. Then we needed to run all the experiments again and blah, blah, blah. And that was why we went away from this. But I think it deserved mentioning because it was a really nice optimization case. So what we continued with was a mesoscale thermofluid metallurgical model of laser powder bed fusion. Here we have the momentum equation. We assumed that the melt pool surface was flat, so we also here included the solidification drag and the buoyancy. And then we suggested a new conical heat source distribution and could calculate melt velocities and temperatures. We compared with a validated against a melt profile from literature, and we got very good agreement. And then we also analyzed the effect of excluding the convection from the melt pool size. And of course, if you exclude convection, you don't have as much cooling as if you include it, and therefore the melt pool size increases when you only have conduction. So we continued with augmenting this model, making it more advanced, including recoil pressure, capillarity, thermocapillarity, ray tracing. And then we combined with a discrete element model, including the particles in a multi-track, multi-layer simulation, quite advanced. So here you see the layer coming down. It's still just a mesoscale simulation. And then you have the laser scanning in different tracks, different layers. And then with this, we could actually predict lag of fusion porosities, and these are the dark ones. And of course, lag of fusion porosities, they decrease as you go along due to the heat accumulation once you scan on something that is already warm. Then we proceeded with a mesoscale thermofluid metallurgical model. Again, it was actually the one from before, but we used it in another case where the energy intensity is higher. So this is where you get the keyhole regime. Now, a keyhole is a very unstable situation. It typically sometimes snatches off and then becomes a bubble. And that bubble could go to the top due to buoyancy, or it could be frozen in by the advancing solidification front. And then you get porosities. And these porosities, we validated the predictions against the surface morphology, and we also validated against these XCT pictures here. And you could see that the model and the images showed, I would say, porosities of similar size and similar distribution and occurrence. Paper 32, coming to paper 32, was a part-scale thermomechanical model. Here you look at a 3D printing of one of these plates here in the corner. That's a rectangular plate. You have the actual scanning. And then what we used was a flash heating. This is where you lump a lot of layers and activate them at once. This means that the calculation time is highly reduced. And we also suggested the so-called sequential flash heating. This is where you get some information about the scanning strategy taken into account. This also suffered from bending when it was cut off from the building plate. So this is the simulation of this. And we could see here that when we used the flash heating, we got something that was almost rotational symmetrical. But when we used the stripes in the sequential flash heating, we got something that was closer to the experimental results that was this. This was the one that was closest, of course, because it had the highest refinement. So via refinement, we get better results. That's not surprising. Then we looked at a cantilever beam that was heat treated. So we wanted to see the effect of heat treatment before removal from the base plate. We did a validation of the additive manufacturing simulation simply by just comparing the tip deflection of the measured part with the simulated part. And they were quite good, so we used that additive manufacturing simulation for taking and transporting the residual stresses into the heat treatment simulation. And the heat treatment profile looked like this, with these material properties. And these are the deformations after printing if you don't heat treat. And these are the deformations after heat treatment if you do, yes, well, heat treat. So we compared this, you see here, the tip deflection. This is after printing, and this is after heat treatment, and what you see here is the experimental finding, and we actually had a very nice agreement, and were able to predict that. So we also simulated, made a little DOE, we simulated the tip deflection as a function of time for different dwell temperatures, and obviously in the beginning it's the effect of the yield stress as a function of temperature that takes place, that's really governing what goes on. Whereas later on, it's the effect of creep, that's the time, you could say, dependent plasticity kicking in. And then the final paper, I can assure you, so there's not that much left, paper 34. There we did a mesoscale thermofluid model of direct energy deposition, a somewhat other, you could say, additive manufacturing process. You see here the incoming powder particles at different points in time. And this is actually a simulation of that from our model, where you see the dynamics of the process. This is pictures of the simulated mill pool. This is the infrared camera of the same. And you see here at the bottom, you actually have made one scan, and then you're turning around and going back. So you, of course, get heat accumulation here at the start of the second track. That, of course, makes sense because you scan on already something which is already warm. And this is what we could predict here. So these were the 34 papers, and I can see that at least some of you are still awake. So we also did some review papers. These are not part of the thesis, but they are even so very important contributions to literature. One in friction stir welding, one in tape casting, 2 in pultrusion, and 2 in additive manufacturing. So I'm coming to my conclusion, where I want to discuss a little about data. Now, there is a lot of people today that say data is the new gold. Data is the new gold. Once you have the data, you have it all. So this has kind of sparked or ignited a discussion between people who believe in data and people who believe in understanding physics. It's a little, you could say, I have exaggerated a little, but it's not entirely wrong, right? So, I want to quote good old John von Neumann, who was a brilliant scientist. He said, with 4 parameters, I can fit an elephant. That's a very nice quote. But then he augmented it and said, well, and with 5, I can make him wiggle his trunk. So I guess that the point here was that don't have too many tuning parameters, don't overfit, because it doesn't make any sense whatsoever. So you could say that today, with our computer power, we have kind of, as I said before, 2 extreme points. We have the people saying the data and nothing but the data, it's all in the data, period. And then we have the more extremes on the other side. I won't say that I belong to them, but I would say I'm probably more there. The data, if they are of sufficient quality, well, they will just tell us the physics that we know already, so what's the big point? But I think the point is that we should combine data-driven and physics-driven models. So we look at our manufacturing processes. These are a physical twin. We get operational data from sensors, our digital shadow, and then we get inductive models. These are data-driven models. But it could be like looking for the needle in the haystack, right? So this is what you see here, a person, and I would say good luck with that. So I think we should combine with the fundamental physics. based on the first principles. These are deductive models. And if we do that, we get efficient, fast digital models that can make way for real digital twins. So it's not one or the other, it's getting the best of both worlds. And you should not, when you do data-driven model, you should not start from scratch when doing these models. You should use the experience from many years of production. You should use the knowledge from the operators actually standing in the production. That is really important. And you should use the knowledge from the physics taking place in the processes. And this could be simple analytical solutions based on otherwise very restraining assumptions. 1D, constant material properties, blah, blah, blah. But still they tell us trends. So we don't look for the needle in the haystack without an expectation. For example, if we scan faster in welding, the melt pool gets smaller. If we sand cast a thicker part, the solidification time goes up with approximately the increase in thickness squared. Something like that. These are simple expectations that our data at least should show something that reminds us of this. And then, of course, we can also run more advanced software to make computer experiments, and these could also be the data, you could say. So, multiphysics models should not just be black boxes where you push buttons and get nice colors. And I love this picture here, right? So it's important that you actually don't just have this argument in the beginning here. So it's important also to have a sound skepticism when evaluating results, and this requires a minimum of physical understanding. It's so important that when you do data-driven models that you have some expectation of what you're looking at, and also common sense. And I would say that's a very, very general statement. Common sense never go out of fashion. Also not in this field. So, I would like to acknowledge all my co-authors. Some of them are here today. You see all the names there. And if you don't recognize them by the name, I have the pictures here. So these are all the co-authors. So thank you very much for that. I would also like to acknowledge the funding bodies for providing the funding for the research. Also like to acknowledge DTU for providing an excellent working climate. And of course also the research infrastructure and the freedom to pursue new research patterns. This is extremely important. And then the third acknowledgement, the two engineers who have meant the most to me, that is my late former supervisor, Preben Nørgaard Hansen. I write in the thesis, in the foreword, I was highly inspired by his friendly and open-minded style and the way that he always took on a new challenge. And then my late father, Eric, I wrote, whose excellent and yet very simple way of analyzing and unpretentiously, and this is extremely important, unpretentiously explaining complex phenomena within mechanics, mathematics, and physics always has inspired me in my research and teaching, and I know at least at the students at DTU, at least at some point also appreciates that I took on from this guy here. So thank you to those two. So let's conclude with my favorite quotes. This was George Box, a late British professor in statistics. He said, all models are wrong, but some are useful. I love that quote, because this is exactly the point. But he also had another one that's not so well known, and I would like to share that with you guys as well. He said, statisticians, like artists, have the bad habit of falling in love with their models. And I would say this probably also goes for many DTU professors. I could be one of them. So my vision is that we combine usefulness with love, so that we actually only fall in love with models that are actually useful. So with this, I would like to thank you for your attention.
Thank you very much, Jesper Hattel, for this run-through of your thesis work, the 34 papers, and a number of inspiring quotes here at the end. It's now time to take a small break. And I suggest that we reconvene in this room 5 minutes to 3, which means that we'll have 6-7 minutes or so just to get some fresh air and get back inside. So thank you very much. And I'd like to welcome everybody to the Q&A session of the defense. And I'd like to invite the first opponent. The opponents have agreed that Paulo Martins will start his line of questions first, and therefore I'd like Professor Martins to join us at the podium.
Thank you. Well, I would like to start by thanking DTU, Vice Rector, Professor Larsen, and the President of the Civil and Mechanical Engineering Department for the very kind invitation of being here today. It's a great honor to stand here today as a member of this evaluating committee, alongside with my colleagues, Michel Bellet from France and Christian Jørgensen from DTU Denmark. I would also like to salute Professor Jesper Hattel and congratulate him on his doctoral technician's thesis, which I enjoyed reading very much. And finally, I would like to salute the audience and acknowledge their presence here today. So it's the first time I am doing a doctor technician's exam. It's in my country there are not this kind of exams. And it's very different from being evaluating a PhD work of 3 years and being evaluated a lifetime work of 31 years, right? And of course that this will also raise the question of who is evaluating whom, right, in this exam, which leaves me sometimes in a little bit uncomfortable situation. But anyway, I'll try to do my best. And my field is manufacturing. I'm not exactly an expert in computer modeling. I know a little bit, but not exactly an expert. And I am going to focus on 3 processes and trying to give a manufacturing perspective and have some discussion. So, of course, it's not the quality of the scientific work that is on doubt. I mean, there is no doubt about that. It's just having a talk about some issues and sharing experience and also learning a little bit, because I learned a lot from reading this thesis. Okay, so I think we are ready, right? So thank you very much once again. So I have this first question that is over there. Oh, no, it's not over there. So now comes the time in which I hope not to fail. Yeah, it's nice. So, okay, so definitely I agree that experiments are important, of course, and nobody has doubts about that. But sometimes I have doubts if experiments should come first or should come afterwards. And that has to do with the level of predictability of the models that we are working with. For instance, in areas that I am more familiar, I would say that in metal forming, I can make first simulation, plan all the experiments so that when I go to the lab, sometimes things are not go exactly as I predicted, but it can help me a lot because I have very confidence in what I simulate. If I am doing metal cutting, and I apologize for people of metal cutting, I have first to go to the experiments, then go to the simulation. And my first question, if it is possible for you to have an answer, from looking at the processes that you analyze, which ones are comfortable in going from your office to the lab, and the ones from the lab to your office, right?
Yeah.
And why?
Yeah. I mean, that's a very good question. I would say, of course, first of all, it depends on the maturity of the process. That's definitely for sure. So when you look at what you've mentioned there, metal casting has been around for a couple of thousand years. And I actually once met people who said, how on earth can you do research in metal casting and in modeling of that? Because it is such a well-known process. But of course, you can optimize and you can make it better by understanding the physics to a higher degree than if you don't do modeling. So it depends. There is no clear answer to this, and I guess that you also know that, because it depends on which phenomenon you want to investigate. If it's a phenomenon that is not a kind of, you could say, very much empirically investigated, and it depends a lot, because you're entirely right that I write perhaps a little too confident that experiments come first. Perhaps I would say experience come first.
Yes.
So it should be perhaps more experience come first when looking at these models, when looking at these processes. So as I also said in the discussion between data and physics, that we need to have some sort of expectation. Mm-hmm. So we need a qualified expectation. And once we have a qualified expectation, and that is in essence always, if you take it to the extreme, based on some kind of knowledge from experiments. So this is kind of what I meant there. So you need an expectation, and then of course you can do modeling. You can do modeling to say, okay, well, how should I plan my experiments such that they will actually reveal what I'm looking for? So some kind of qualified idea of what you expect to see will make you, or what you want to investigate, will make you able to make a plan for computational experiments that can support you, give you some idea, and then you go in the lab, and then you have a process window, then you have an expectation which is much better as if you didn't do the simulations and the computations. So that's beyond discussion.
Yes.
Yeah.
Thank you.
Mm-hmm.
Now, I hope not to make a mistake. Oh, yes, that's good. So now we go. I mean, this question here is maybe a little bit politically incorrect, but anyway, I think I should put it. So I like very much analytical models.
Yes, me too.
But because when you look at equations, you can feel the effect of the parameters instead of doing random simulations or whatever,
exactly,
right?
Exactly.
Now, but as much, I mean, I'm sure you agree that during the past years, we see less and less analytical modeling being proposed.
Yes.
Perhaps the answers are on my questions, right? Is it because the phenomena that we are analyzing are becoming more and more complex? Mm-hmm. Is it because numerical models are so powerful that they don't provide a fair competition with analytics nowadays? Mm-hmm. Or the political incorrect phrase, the last one, which is there is, in my opinion, the mathematical background is unfortunately, I mean, there are exceptions, of course, but it's going down in many fields.
I think that all three answers or possibilities or options, they are actually explaining what you see there. I mean, I also love analytical solutions a lot. And you could say it's for verification. You need to check in your numerical model, are the equations solved right? The only way to check that is against an analytical solution. But that's not the only purpose of analytical solutions. And I think one of the slides I showed there with the data versus the physics-driven models, that in analytical solutions, you have already a compact DOE.
Yes.
Because you can say, if I change this and that parameter, you can evaluate that immediately, how that affects your result. And this is why analytical solutions are so good to gain understanding from on how the process actually works. But, so, it is a combination of all the three. Let me start with a small tale regarding the last one. It is a course in manufacturing engineering where I teach heat transfer. It was Coroner's Rule, where it was about finding out that if we cast something that gets 10% thicker, and as I wrote in one of my slides, it actually squares. The solidification time squares with the increase in thickness. The thicker it gets, the more time it takes to solidify. Not surprising, but actually the increase in the thickness is squared. Now, this was 10%. And I gave the students this small task, and I said, okay, if you have a cast part, you increase the thickness by 10%, how much longer time will it take to solidify if you use Coroner's Rule? It's 1.1 squared. Then a lot of the students start maple, right?
Yes.
So they start, and I said, okay, try not to use maple for this. And this is exactly what you say here. Most of them, I mean, they can do it. So it's not a critics of using maple. It's a critics of using maple for the wrong problem. And this guy, and then I said, okay, well, it's actually 1.1 squared. And then I said, it's 11 squared. Could you do this by hand? And no, it was. And then I said, okay, well, what's 10 times 11? That was 110. And then you add 11 on top of that. That was a challenge. I want to say I'm exaggerating, of course. I'm not exaggerating. I'm exaggerating how much he was representing all the students, because he was not. But the point is that you have a point there. That's for sure. But I don't think it's the only point. I think it's, of course, the growing complexity of the phenomena, but definitely also the advances in numerical modeling. Because this means that we can kind of simulate everything. And it goes a little in hand with the story about the data. Because you could say that today, okay, but it's all in the data. So what we only need is statistics to understand the patterns. We don't really need the analytical solutions. And by the way, if we want to solve all the advanced physics, we have all the numerical models in the world at our disposal. So why on earth get to know analytical solutions? So I think it's a combination of the three.
Yes, thank you.
And sorry for the small tail. Yeah.
Okay, so now I have to explain exactly how I analyze your thesis. So I analyze your thesis of course I read the thesis, that's not the question, but there were different strategies of analyzing the thesis. And what I did was I took 3 processes, and for each process I tried to identify which are the challenges. And how are you dealing with these challenges in your thesis? I think it's another way of analyzing. And in friction stir welding, the bold ones are what I consider the challenges. Maybe I'm skipping some or forgetting, but I think more or less they should be there. And then comes the first one, which is material behavior modeling. And I gave an example there. And so in this particular paper, although it's an aluminum T3, which has been natural aged and should be certain stable metallurgical condition, but still you may have some aging with time. And the point is you are using a reference from a book which does not provide you a total guarantee that the material conditions are exact, the flow stress is exactly the same.
Definitely.
So why not doing more material characterization on this kind of models so that you can characterize your own materials? It's time consuming, but gives you a more...
but that's true. I think the reason for doing this was that, I entirely acknowledge that we looked up a lot material data from literature because we wanted to focus on the modeling parts. So that was a deliberate choice. But of course, it has the drawback that even though we make a very advanced model, that takes a lot of different, you could say, physical phenomena into account, it still runs according to the GIGO principle, right? Garbage in, garbage out. So if we don't have, you could say, realistic material properties, then of course that will be reflected in the results. But our aim was more to look at literature and say, okay, well, what has been given as regards the more fundamental, you could say, contributions in the modeling part, yes. Which meant that it was a deliberate choice that we didn't perhaps do an experimental campaign that would have been needed. So that's beyond discussion.
Yes, thank you. Now, now comes one paper I like very much.
Yeah.
This paper of analytics on friction steel welding. I like very much.
Yes.
I like very much the different zones of sliding and sticking. I really like it. But when you go to the heat transfer, only when it's sliding, you depend on the experimental force. And my question is, why don't you formulate it so that you could get some guess from analytics and try to put there? Because if you do that, your model is 100% analytic.
Yes, that's true. That's true.
If you don't depend on the experiment.
Yeah, but it's, I mean...
I think you could do that.
Yes, right? Yes. You're entirely right that it's not, when you ask the question, how analytical is the model? I would say it's mostly analytical.
Yes, if it is sticking, it's fully analytical.
Yeah, exactly, exactly. But here you need information about the force, right?
But I think you could get it.
How would you do that?
Well, I think you could have, in practical terms, there is a deformation, so there is a kind of a metal forming approach.
Okay.
And you could get the pressure and multiply by the projected area, and you would get an estimate of force.
True,
right?
True. That's true.
So I think that could be done.
Yeah. Yeah.
But it's just a comment. Again, I enjoy very much this paper.
Yeah. I want to say that I think it's also because in literature there were contributions along these lines, and they also used this experimental force.
Yes.
So what we wanted to do was to say, okay, well, we have actually from very well-known people in the field, there were 3 or 4 contributions. From one with sticking, sliding, one with including the probe, one with not including the probe, and so forth and so on. So then we said, okay, well, let's try and unify all those models by looking at more fundamentally what happens in the interface when we have the heat generation, what happens when we have full sticking, what happens when we have full sliding and partial sliding sticking, and then trying to analyze this in a more systematic way. And then we ended up with these analytical solutions, or this, you could say, unified analytical solution that actually entailed all the others.
Yes.
And I think that was really interesting in the sense that people had only looked at special cases, and now we came with this. And I think that this is probably also why this is my most highly cited paper with more than 1,000 citations.
Yeah, it's a very nice paper. Yes. Okay, good. So maybe I cannot go to all my questions because I will not have time. So I had a question here, but I'm not going to pose. Just to say that this is a beautiful experimental paper.
Yeah.
I enjoy very much. This is not only a question, it's just a small note. It's not the volumetric strain rate, but the effective strain rate.
Oh, yeah.
So there is a TPO there.
Yeah.
And now we come to this kind of simulations. And I mean, we were talking a moment ago, and when we look at the work of 31 years, it's interesting, and reading back the papers is interesting to see how you evolve in analyzing the processes.
Mm-hmm.
I mean, you start with simple models, and then you're making more and more complex. Of course, that has to do also with the evolution of science, right? But I want to go back to the first models because although they are simple, the question is, can we still use them? There are limitations, and what is missing, and so this kind of discussion. So I went back to one of your models, and This is basically simulating friction stir welding as a heat source, right?
Yeah.
And you have some coupling with mechanics, with the mechanical equations, right? Small deformation. And I was not totally sure if this coupling was only at the end or if it was during the process. I don't know. I could not.
This was a one-way coupling.
Okay.
So this was a one-way coupling where we solved the thermal problem first,
and then you unload.
And then we load that into the
mechanical,
mechanical calculation. This was as opposed to the one where we saw the rotating tool.
Yes, I will go that later.
Yes, because that was an ALE, fully coupled ALE formulation.
Yes.
Right?
And that one takes into account geometric nonlinearity.
Exactly.
And this one only takes the material nonlinearity and the boundary conditions nonlinearity. Okay.
Yes.
But still, if I mean, your experience, this is much faster, right?
Yes.
How accurate can we expect these models to be, right? Can we use them for daily use, or no, because don't have the geometric nonlinearity of the material going very high deformations? This will somehow create problems in the predictions of residual stresses. Or, yes.
For sure. So I mean, this model that you refer to there is, I would say, more like a standard quasi-steady-state thermomechanical model in computational welding mechanics.
Yeah.
So this is what it is.
Yeah.
But the heat source is not the typical Goldak heat source, of course. It's the heat source that we derived based on the analytical solution with experimental observations from an experiment with either the force or in the other case the fully analytical.
So it was not a Gaussian.
No.
Okay.
No. So this was actually the heat source that we derived in previous papers. Yes.
Okay.
Yes.
Okay.
Yeah. So, of course, relevant for friction stir welding.
Okay.
Yes.
So because of that, because of using the unloading, I would say in the end, when I was looking at the evolution of residual stresses longitudinal, depending where your probe is, you have different patterns, right? Because you may have, when it's heat, you get the pattern that typically is in this side in the top. Then when it starts cooling down, and then when it's cooling more down. And when I look at this paper, it's everything the same color, so it's because it's done in the end, right? Unloading residual stress is just in the end of the thermal calculation, or you do thermal stresses during the heat source movement?
Well, it's a sequentially coupled model in the sense that you calculate temperatures and you calculate the thermomechanical or the mechanical problem in which you solve the equilibrium equations, you get displacement, strains, and stresses, right? So there is not a coupling back from this simple model. This simple model, the temperatures are not depending on the mechanical solution. But it's, of course, a transient. I mean, it's a quasi-steady state in the sense that you send results from the thermal calculation into the mechanical calculation, and you go like this in time, and then you get these results, you could say.
Although I would expect to see not a symmetric one, but to see residual stresses.
But of course. But this is because this is based on the analytical heat source. And the analytical heat source doesn't take the rotation into account. And this is why it gets symmetrical. But if we use, and this is what's tricky about friction stir welding, because we also made CFD models. And there we see the flow. And then we did the most advanced model that was really, really advanced at the time, and actually still is, where the interface condition in a thermomechanical ALE simulation is part of the solution itself. And that could calculate residual stresses really on the fly, or I would say transient stresses, because they are not residual before you're finished, right? So that could do that. But because of calculation time, what I showed there to the right of this one was it was plunging, going down, and then moving a little, and then it died.
Yeah.
Because it was 20 years or 15, 20 years ago, and that was so, you could say, demanding computational-wise. But this is why you don't see something which is asymmetrical, because it's based on this, but still new, you could say, heat source that was based on this analytical...
When these papers were published, this was novelty.
Yes.
And that's...
Definitely.
I mean, we are analyzing 30 years, right?
Yeah. So that's the reason why, it was symmetrical.
Of course.
Yeah.
Okay, so this is not relevant.
This, of course, you already talk about it.
Yes.
I like it a lot, this one.
I
had several questions, but I would like just to focus on...
What do you think? Do you think there is some effect of mass scaling?
Yes. We saw that.
Okay. Because
there is an effect
I have
of mass
this
scaling.
fundamental problem about dynamic explicit.
I mean, of course, if you use a dynamic explicit method, you have a, you could say, a stability criterion with the CFL number and all that, and the Courant-Friedrich-Levy number, and then in the thermal calculation you have the Fourier number, right? And they are kind of.
You can, in this case, you can overestimate the contact forces.
But for sure, because when you do mass scaling, it's in order to be able to use a higher time state.
Yes, but it's very nice, very nice paper.
Yes, and then what we did was that we actually we made an investigation of how much the mass scaling means also for the kinetic energy, and we were kind of within the recommendation limits. And that was why we said, okay, well, we mass scaled at the amount that we did, but we assumed, or we kind of realized that it was within the recommended limits, so that was kind of admissible or doable. Right?
Okay. So now I think I need to...
Perhaps I could mention with this paper, there were some people that once from a journal sent a paper to me for review, and Henrik Schmidt and I, who made this paper that we were sent for review, was almost a one-to-one copy of this paper.
Oh.
So we rejected it, and then it appeared in a journal, in another journal 4 months later. So that was just a comment. That was.
Okay, I will check now process, because otherwise I will be. And we go now to, doesn't matter this part, we go to additive manufacturing, which is my second one. So forget about the question, because it's the same question about material data. Forget about that. I just want to, now for me, I think those are the topics, right?
Yes.
And so I will forget about the first.
Yeah, because my reply would be the same.
The same, yes. And now we are talking about this pseudo-analytical. I had a question about this one, but you already answered it, because you said that when we go to complex parts, forget about this pseudo-analytics. My question is out, so I don't have this question anymore.
I actually have 3 slides explaining this pseudo-analytical method, and I would love to show them, because if you are interested in numerics, you can see how beautiful it is. But it's not general, for sure, because we needed to be, because I can just elaborate a little. It was the thermal part was a relatively simple, that was a thermoceutical, you could say, analytical model. But then we needed the mechanical model, and say, how severe is this thermal field when it comes to thermal deformations?
Yes.
And there we did a lot of experiments. Sankhya sitting over there, he was actually doing that very nice work, and doing experiments also and calculations to see how can we define a thermal fitness number that gives us information as to how willing it is to deform. And that thermal fitness number, of course, is problem or experimental dependent. So we tried to make it general, but of course it is, if we were to build some valve or some very complex structure with 3D printing, additive manufacturing, using this method for suggesting the scanning strategy would probably not work.
That's why these two questions, they are not relevant anymore because you already addressed them.
Yeah, good.
Now, this is a part that I am particularly interested. Together with Chris, that is over there, we have been developing our finite element code 2.1, which is, as you know, another additive manufacturing process, another category, wide arc additive manufacturing, which is a little bit more macro, I would say.
Yeah, sure.
And I think that when I see the mesoscale modeling, and these papers I read from you, I learned two things. And my problem is, the mesoscale modeling allows us to model very small amounts of space, very small amounts of time with a lot of computation time, right? And of course that they are relevant for understanding phenomena that occur inside the molten bead, right? Because you cannot model them with macro analysis.
Of course not.
But for me, manufacturing point of view, I would like to understand why there is lack of communication between the meso world and the macro world. In the sense, let me be a little bit more clear. So I learned from your thesis that if I do the simulations without taking into account convection of the fluid inside the bead, I get overestimation of temperatures.
Yes.
Right?
Yes.
So I said to myself, okay, this is something I was not aware. So probably in my macro code, probably because I don't have convection, the way I have to do this is probably increase the conductivity inside the bead so that somehow I can compensate.
Exactly. That was exactly what I was going to suggest. Okay, this is what people do. Yeah.
Check. Yeah. I understood. I found something in meso that helps me in macro. Right?
Yeah.
Check one. Now, check two is this very interesting flow inside the bead where you have material being pumping to the back, right? And when you are using, like myself, I am using a gold.
This is the well-known double ellipsoid.
Yeah.
Yes.
So I said, okay, that's okay because somehow that's why my ellipsoid is longer in the back than in the front, right? But the point is, how can I use that information on the flow in order to adjust my parameters? So it's a difficult question, but from a macro sense, what I would like, I just learned that I need to increase conductivity.
Yes.
And the second thing, I don't think there is an answer for that, but can I get a better shape of my Gaussian source with the knowledge I get from meso? Because meso is allowing me to understand porosity and to understand this phenomena that you show, amazing simulations. Yes. But from a macro point of view, how much can I export from knowledge? I would like, if possible, to talk a little bit. It's a difficult question, I understand.
It's a very good question. Sorry. First of all, the Goldak double ellipsoid is a phenomenological model that you use in order to simulate, you could say,
the power source.
This heat source and what you actually see experimentally. And then you say, okay, well, how does it look like? If I weld like this, I get a tail in this direction, and then I have a steep gradient on front. How do I model that? Well, I model this with the Goldak double ellipsoid, and then I ensure that when I integrate the heat intensity in this, I get the total heat intensity in my welding process. So this is how the double Goldak, or double ellipsoid Goldak suggested there some 40 years ago, how that works. Now the question is that can you then combine with a model like what we did here in additive manufacturing, where you have the laser, and then we suggested this with the conical shape, with all that, with the intensity, with the absorption and all that. And then can you then get information about from such a mesoscale model that you can put into this macro scale double ellipsoid Goldak model? This is what you're asking, right? And I would say that typically what you do with the Goldak double ellipsoid is that you calibrate it such that it looks like experiments or observations of any kind, and then you say, okay, well, of course, this will, I mean, this will be, you could say, affected by process parameters, by welding speed, blah, 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 and so forth and so on, material properties as well.
Yes, and efficiency of transfer.
Yeah, of course, of course. So it's quite difficult to take a mesoscale model and then import results into the Goldak double ellipsoid if that is what you would like to do. Yes. You can, of course, adjust it, simply just run a small DOE and then adjust it towards what you see in the mesoscale model. And then say, okay, well, this is what I would do, and then that's it. But I don't think that you can actually get it any further because this is a very phenomenological model at another scale.
Yes, yes, and the bad story about this is that in meso we can understand the physics inside, but we cannot model a part. Right,
yes,
the real part.
Yes, and
so we have this problem of. One is good for one thing, the other is good for another thing, and we would like somehow to be able to connect them.
Yes, yes, and this is exactly...
Which maybe will happen in a couple of years.
I'm pretty sure that it will, and there are people actually trying to do that.
Yeah.
And actually what we... I have a slide also, if I could... Pardon?
Creating some RVEs.
I was exactly going to say that, because I have a slide in my additional slide deck of 50 or whatever, where I have exactly this, and it's also written in the conclusion where I say how to get that vision to become true is actually making RVEs, where we also look at grain morphology and we look at you could say at this micro scale mechanics, and then we import those into part scale models in additive manufacturing. I think it's in the third or fourth last page in the conclusion. I give that figure, right? Yeah. And this is what we have to do, but then comes the question, what is the size of a representative volume element?
Yes, yes.
And this is always the question, right?
Yes.
And where should it be taken?
From where? From where?
Right? So the size and from where. And I showed actually an example of this, and that was in the paper 3 and 4, where we had the ductile cast iron, where we did a representative volume element, you could say, and got some better results. But what really worked was that we took the real microstructure from the you could say from the sample and then enmeshed that in fine element, and then we got 3-4% you could say deviation from experimental observations, right?
Can I just ask one thing? How is my time?
35 minutes.
Okay, so I will skip some because otherwise we'll focus always in the same kind of things. I mean, this is a very nice one.
Yes.
And
we compared with experimental observations.
The problem is the CPU time, right?
Oh, yeah. It took forever.
And the transfer between models, but it's a beautiful one. And now we go to the macro, back to the macro of LPVF, right? And now I am happy of working with WAM, because in WAM I can adjust the size of my mesh to be more or less compatible with the size of the drops. So I am on the same sort of scale.
A drop. Which process was that you talked about now?
WAM, wire additive.
Oh yeah. Okay. Yeah.
So that is beneficial to my modeling, but here there is a problem because your depositions, they are very thin, right? So you cannot rely on your mesh, because otherwise, if you are meshing layer by layer, it will be a nightmare.
Of course.
So you need to do, and it's what everybody does, you need to accumulate some layers and accumulate some widths, right?
Yes.
And there are two techniques. One is the flash heating that you explain in your thesis, that has difficulties in, and we understand why, because everything goes like that. Yeah. So for me, there is no gradient of temperature, and therefore the possibility of taking into account the direction of the deposition does not exist. No, and you get the symmetric, symmetric thing, and you show that the deviations in the deformation, they are very high. Yes. And then we go into the possible one, considering CPU times, which is the sequential flash heating. Yes. And now comes the difficult question, which is you show that in this particular case, you clearly show that there are certain modeling sizes that work well and others that don't work well. Yeah, but the point is, how can we generalize this for a part that you didn't make the experiments first, right? I mean, here, I can see that the 1.5 and 3, they work very well. Yeah. But is this telling me that if I use sequential flash heating with laser powder bed fusion, should I rely on 1.5 or 3, or is this part dependent? What is your vision about that?
I would say that's a very good question. It's very difficult to answer. I would say that the purpose of this paper was to, first of all, make some more fundamental analysis of the time frame during which we have the flash heating turned on, because it means a lot for the residual stresses and the plasticity that takes place. Yes. Because some people use gradual heating. I mean, because what you need to do is you need to say, okay, flash heating, and then we have the real process, and then we have the scanning, and then we have the energy should be the same. Of course. Yes. That's point one. Yes. So the energy should be the same. But the way or the time it's deposited is extremely important, which means that what we wanted to investigate there was how long time should we deposit, should we have the flash heating turned on so that we get sufficient high temperatures so that it yields due to high temperatures, and we get sufficient plasticity and you could say realistic residual stresses and deformations. Some people in literature do gradual heating. So they say, okay, well, the flash heating, it just takes the time that it takes to scan the whole lot. And this, of course, doesn't work at all because it gets 400 degrees warm. Yes. You still get the right temperature, but you never get the right deformation. Yeah, and
some people use this inherent strain, which I never understood exactly how that works.
But I could
think
perhaps,
it doesn't.
I have seen some results from inherent strain.
Guess?
You have to, what you have to do is the way I understand it, is that you have to make some experiments first. Oh, yeah? Okay. Yeah, and then you print in 0, 45, and 90, and then you measure the tip deflection or whatever, and then you translate into plastic strain or whatever. This is what some people do. And then generalizing that is like generalizing our scanning strategy where we optimized. Yes. I would just say good luck.
But because on that strategy that we are talking about, not this one, there is a fundamental problem, which is when you get residual stresses, it's not because of the calculations you do, because you apply the same thermal strain everywhere, right? So you don't model the residual stresses coming from the process, but something that you apply the same thermal stress everywhere, which is not correct. And I think in those cases, you are more getting profiles from removing the supports than from the process itself. You understand what I mean?
Yeah, I entirely understand. But you have to realize that when you build something with flash heating, there is a difference.
No, with the inherent.
Inherent strain.
Okay. I was talking about that. I was talking about.
But what you can do in inherent strain is that you can also, instead of doing experiments, you can do computer experiments. Yes. And then you can make it based on computer experiments. Yes. But of course, generalizing the inherent strain to a very complex 3D shape, that is, I would say, quite questionable.
It doesn't work.
I don't know whether I would say it doesn't work, but I would say at least it gives you some results.
Yes. Complex. Complex, yes.
Yeah, yeah. And then I would just comment on this paper. It was interesting to see, we wanted to see, okay, what about the time? How long or how little should the time where we use during the flash heating be, during the sequential flash heating, and then see how much did we actually need to resolve the scanning just a little to get something that deformed like this.
Yes.
So trying to extrapolate a general recommendation out of that paper, that was not the idea. But I can certainly understand your question, but I would be very cautious with making some kind of general recommendation based on this.
Yes, yes.
So it was more like a thorough analysis of the method, I would say.
But if you do macro in laser, there is almost no other alternative.
No, that's true.
So
that's true.
Yeah. Okay, so now maybe one more about this. Yes, maybe. Now it's this. I mean, you show this one.
Oh, yeah.
And so you have deposition, then you have thermal heat treatment, and then you have release of supports, and then you have a deformation, right, coming from residual stresses. But everything is combined, and my question is, how can you separate the residual stresses from the deposition and heat treatment?
But we don't.
I know, but it's difficult to separate the three phenomena, right? Because they are coupled, right?
Yeah, yeah. So what we did there was that
what is the most relevant? Right?
Yeah. Okay. So what we did was that we simulated the 3D printing process of this, including the supporting structures. That was simulated in layers with a sequential flash heating method, I think. And there, of course, you do get locked-in residual stresses from the process because you have a thermal history, and so the temperatures are varying in, you could say, in time. And then you calculate the transient stresses, and then when it cools down, you get the residual stresses. And the way that we evaluated this was that we compared then that residual stress calculation of the AM simulation, before the heat treatment, of the AM simulation. Because
with the experiment.
With the experiment of the tip deflection.
Before releasing. Okay. And then you compare after releasing again. Okay. So that was my question.
Okay.
That was the way I would do.
Yeah.
Okay, good.
Okay, good.
Very good. Very good. Okay. Oh, sorry. Yes. Now comes pultrusion, which I must confess that is a process that I am not very much familiar. So I think, again, those are the topics, but maybe I'm wrong because I'm not very much familiar with this, but maybe. And your paper 21, which is the first one, is based on this. You were compared with some paper on the literature data, which was this one, right?
Yeah.
And I can't remember the author, Valiapin or something like that.
Yeah.
Something like that. And then you made a model like this one, right?
Yes.
Now, I have a couple of questions here. As you said, and in the paper of Valiapin, it doesn't tell exactly where the ethers are.
No, exactly.
Yeah, so there is nothing said about that, just the temperature, which, I mean, a paper should be replicable, and it doesn't provide information for others to replicate the work he did. So we know the temperature, but don't know exactly where the heaters are.
Of course, and then we did an inverse analysis to see, okay, where were the heaters, what was the temperature, and that was kind of the idea with that paper.
Yes, and the point is, of course, you simulate in 2D, right? In the axisymmetrical one, which is not exactly, and maybe that's because of that, you only compare in the center line and not away from the center line because maybe you had some border effects on the, maybe, I don't know. Now, the point is, when you do the inverse analysis and you get this very good correlation, it's excellent correlation.
Yeah.
My point is this the only possible solution for the position of the ethers?
Of course not.
Okay. Yes. I
am
happy with
citing good old John von Neumann, with 4 parameters, I can fit an elephant, right?
So that is one possible solution.
Oh, yeah.
One possible solution.
It was in order to show this was an example in literature of this that nobody else did.
Yes.
And that was kind of the novelty, but we didn't claim that this must have been the solution of the position of the heaters. No way.
Yes.
No, I mean, an inverse analysis is, of course, like an optimization problem, where you minimize you could say, a difference between experimental and modeled results.
Yes. Okay.
And a lot of combinations can lead to equally bad results. This is one way of stating an inverse problem, right?
Because what you show is that if you use just one thermal resistance, you go nowhere in terms of comparison with results.
Yes.
And that is expectable.
Yeah. But this is actually, and that was the reason why this had novelty, because this was what people did in literature. Because they only used a constant heat transfer coefficient at the very length of the die, meaning that the thermal resistance was constant.
They did not even took the die into account, because that was a boundary condition on the composite.
But that boundary condition could be seen as a prescribed Dirichlet condition or as a seen through a heat transfer coefficient. And what we wanted to show in this paper was that assuming a constant heat transfer coefficient, the entire length didn't make any sense. And then we suggested something that was better, but not the only solution.
Yeah, okay. Very good. Now this one is the 3D advancement, right? You talk here about different integration schemes and compare with another paper. I will skip that. It's okay. I enjoy that part as well.
What was igniting this paper was that there were some people in literature that compared a standard extension of the 2D ADI thermal solver with a 3D finite element solver. And a standard extension of the 2D ADI solver makes absolutely no sense because it's only conditionally stable.
And you did in a different way.
And then we took the right one, which was the Douglas gun one, and then we showed that this was actually faster than the finite element model.
Because you compare with this paper from Careto, I think.
Carlone,
Canon or something. Carlone.
And they compared those on unequal terms. So that was, I would say, close to nonsense. Of course, they would find that this 3D extension of the symmetrical ADI would not match a finite element. So we wanted to show that this could be done, and actually the right way.
Okay. So now it's just a comment. You see, as I told you, your processes, the way you handle them, they have an history, right? You start with more simple models 30 years ago, naturally, and then you go more complex. And in most of them, you jump into meso, right?
Yes.
And my question is, why didn't you consider the meso inside the resin injection chamber?
Yes.
In this process?
Yeah, that's a good question. That would entail, of course, somehow a CFD model, a flow model, for sure. And
would you get any benefit from doing that? Do you think you could get any important information?
Well, one could say, of course, the overall flow is the fact that, the overall is the advection. You have something moving. Then you have some backflow, and you have some local flow. And
the chemical reaction.
Exactly, and then you have the chemical reaction that does like this, of course. And then I think the most important part is to get the overall flow right so that the chemical reaction, the advection term also on the curing, becomes right, or at least realistic, so that you get the curing and you could say, the transient evolution of mechanical properties described at least in a way so that you get residual stresses realistic. This was at least our aim, because we saw in literature, first of all, there was this nonsense with the 2D ADI, then we had to correct that. But then there was the other one with the thermochemical mechanical models. There were absolutely no one who did that before. So we said, okay, let's focus on thermochemical mechanical models. Chemical in the sense that we have curing, And then we have a pure kinetics model, and that is activating a source term in the heat conduction equation. Then we have the advection term, and then we couple this with the mechanical simulation where we calculate displacements, strains, and stresses, right? And this was a huge contribution in literature at the time, so that was why we didn't go for the CFD, you could say.
Yes.
Mm-hmm.
Okay, the time? Okay, so I will close. I'm just going to, so I skip this one. And I go, this is not a question, it's just a comment.
Yeah.
I like very much papers 25 and 26.
Yeah.
I really like them because they go from the modeling to the industrial application, and they are very interesting papers, and the results are very good. Mm-hmm. So I enjoy very much reading these two papers. And
thank you very much.
Very. I mean, I enjoy reading the thesis, but these two papers of conclusion, I really enjoy a lot. Okay, so I came to the conclusion. Well, I have this here, but let me so summarize. Of course, that this is a very excellent work, and with underlying knowledge about physical phenomena of different manufacturing processes, and giving important contributions to the advance of science and technology of manufacturing. And the coupling with multiphysics, it's not easy, and it's not everybody that can do that. So you need to be someone exceptional to make this kind of coupling, and I give you my congratulations on that.
Thank you.
And finally, once again, I would like now, I will make the thankings in the reverse. So I start by thanking my colleagues of the committee and Professor Hans Hansen for the invitation. And finally, Vice Rector, Professor Larsen, for the invitation of DTU. It's quite an honor to be here today, and which I will take for extending my staying, to stay with my friends until Saturday. So thank you very much, and very excellent work.
Thank you very much.
Yeah, you can. Sorry. Thank you. Then I'd continue with the second opponent, and I'd like to invite Professor Michel Bellet to the podium.
Så I må lige hjælpe, hvis jeg skal skifte til nogle andre slides og sådan noget. Ja.
Var det den her, du lavede på?
Ja, blandt andet. Ja, men både den der, men også de andre, ikke? Hvis, ja. It's just some extra slides if I need.
That would be useful. That would be quite useful. Thank you.
Ja, der er ekstra slides, og så er der den oprindelige præsentation. Så er der papers. Yes.
Okay. So good afternoon, everyone. I hope you are still alive, not too tired. So, of course, I would like first to replicate the thanks, many thanks for the invitation. So many thanks to DTU professors and members of the committee as well. I don't want to repeat, okay, but really I felt that it was quite an honor and a pleasure at the same time to be invited on such a special opportunity. So thank you, Jesper, to have
thank you, Michel.
Certainly solicited and nominated me as a potential referee.
Yeah.
But it was it was with pleasure that I dived into your contributions. Very, very interesting. So I think the first time we met, it was probably 98 at MACWA's conference on modeling of casting and advanced solidification processes. It was probably in San Diego.
It was in San Diego, but I actually think that you were also in Davos, right?
I was not in Davos, but
Okay.
I was in the maybe the second one. Maybe it was in London.
Yeah, I was not there. Yeah, okay,
yeah.
But then it might have been in '98, but I remember Davos in '91. Yeah.
Yeah. So we know each other for a long time.
Yes, very much.
But we have not really worked together.
No.
So there is no conflict of interest.
No, not at all.
Okay. Well, so it's a difficult task for me. So I'm not so organized as Paulo. So thank you, Paulo, also for sharing the job, because of course it was a huge task. 34 papers.
Yeah. I just want to say
in total. No, but it's just a thin book.
Yeah.
But when you group all the papers, you have 700 pages that you have to evaluate.
Yeah. Yes, I probably overdid it a little. I got carried away. It only took 4 years to write it, so yes. Yeah.
So thank you, Paulo. We made an agreement to share the work, but anyway, it was a hard job. So I am less organized than Paulo. I am not able to display my questions, and I have not prepared my questions so well, actually. So don't be afraid if I go back to my notes in order to ask the potentially good question. Okay, but maybe I have a question on the format of the thesis. This collection of papers plus the book. Okay, so is it a personal choice, or is it the format as required by DTU?
I think I would say quite much it's a matter of personal choice. Like I discussed with my head of department, that one could argue that I made a paper-based scientific monograph, whatever that is, right? Because either you make a paper-based thesis and then you write 45 or 60 pages about that, or you make a scientific monograph where you go through a lot of papers, and then just to be on the safe side, I did both. And that's why you guys really had a hard time reading all those 700 pages, right? So, like I said, sometimes when I do science and I write something, I can get carried away. And I got carried away because I thought that, well, it has to be explained thoroughly, right? And I would like to introduce all the papers as well as the reasons for actually choosing those papers. I do that in the beginning. I write about, well, there is heat transfer, solid mechanics, blah, 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 finite differences, finite volumes. I would like to tell a coherent story within each of these 6 manufacturing processes. And I also wrote, and I think that's a very deliberate choice, because when you want to write something like this, you can also write it based on, you could say, field. One could go with heat transfer, and then CFD, and then solid mechanics, and then material science. And then so trying to write a coherent story that is interesting to read, or at least I imagine myself, it could be doable, let's call it that. I don't know whether it was, but anyways, giving it so much structure that you could see, okay, well, here we see that the methods are to some extent generic. And this is why I, in the beginning, just present some of the simple equations for heat transfer, solid mechanics, and CFD. Not advanced, but just the simple, you could say, first principles balances, and then a little about material behavior, but not much. And then the deliberate choice was that when I went into each of the single processes, metal casting, then I added a little equations and friction stir welding, and then referring back to, okay, this is actually equation 2 for the basic heat transfer equation, but then we need some convective terms, or then we need, and blah, blah, blah. Because then I gave an introduction in the beginning to the, you could say, the theoretical modeling of this, and then I tried to refer back to that in each of the chapters regarding the different processes. So that was a deliberate choice, and I also wanted to write it a little in a storytelling style. I hope that you appreciated that. Definitely. Because this gave a quite, you could say, straightforward way of understanding the overall idea of the papers, and then one could go into the papers and look for details, right? Yeah. So that was kind of, but no, it's not required by DTU to do it like this. Okay. I think I got a little carried away. But of course, also the choice or the amount of papers, I don't know, 34, is that a reasonable number? Should it have been 50 or should it have been 15? I don't know. I think you would have preferred not 50. But anyway. So.
No. What was interesting was the progress in each of the 6 topics.
Yes.
So that I think that was very nice.
Yes, because I tried to start out with some simple models, and this was exactly what Paulo said, as well, that in the beginning we did some more simple stuff, and then we proceeded with more advanced stuff, and this was actually what we did in all of the 6 process groups.
So in fact, first I read the book.
Yes, or the booklet.
Booklet.
Yeah.
And then of course I was saying, well, they asked me to act as an opponent, so I must go into the details. So I must go to the 34 papers, and then I alternated. When I finished a series of papers, I came back to your synthetic document, and I really appreciated that, because it introduces a perspective.
Yes.
So it was very nice. Okay, so the grouping by processes was quite relevant. It was the only solution, I think.
I think it was the only solution.
Yeah. Otherwise, it would have been boring.
Yes.
Yeah.
I'm happy that you say otherwise it would have been boring.
Yeah. So, of course, we understood that what makes the strength of the defense today, we realize how wide is the scope of your expertise. So, computational, mechanics, fluid flow, metallurgy. No, so no problem on that. Okay, so maybe we can start with casting. If you could display a slide on those very big castings. It was the first 2 papers, in fact, I think.
Should we just look at the slides or the papers? The slides?
The slides, yes, the slides is enough.
Was it open here? Oh, it is here. Extra slides. Extra slides. They're all extra slides. Oh, here it is.
Yes. Okay.
I think it's this one, and then we should go back. Do we have the clicker here?
Sorry.
Then I need my glasses, otherwise I cannot see anything. So let's have a look here. Okay, it's going to take some.
Back to the future.
Yes, Back to the Future, exactly. Yes.
Okay. So the purpose of those 2 papers was about Meso-segregation.
Yes.
Mostly.
Yes, and centerline porosities.
And centerline porosities, for which you use the
Niyama criterion.
Existing criterion, directly deduced from heat transfer.
Yes.
So you proceeded to mold filling analysis. It was Navier-Stokes equation,
this is what
simulation of fluid flow, and then cooling down.
Yes.
Simply.
Simply, because of course it is Navier-Stokes, but it's not at the scale that's actually needed to investigate this.
Yes, exactly.
Yeah.
So that's a simple model.
Yeah.
And from your introducing slide, a simple model could be a good model. A good model.
Yes, exactly. Yes.
And you prove that amazing results can be deduced from that in order to optimize the processes.
Yeah.
So I had a question, however, because those criteria, Suzuki...
all of them.
Okay, we know, and of course, after 30 years more, then there are first-order approach criteria.
For sure.
So, and my question was, why didn't you go deeper in that field, trying to solve in a multi-scale analysis what is exactly macro segregation, what is meso segregation, trying to couple fluid flow at small scales and so on. So did you have this opportunity, or was it difficult to find financial support to get new PhDs in this way?
Exactly.
If you could tell how this happened, it would be interesting, I think.
So this was a PhD project with a Czech PhD student, Peter Kotas. And we had this, you could say, idea of trying to solve and optimize, getting rid of some of these defects with you could say, a reduced order model, or at least a model. Because
I have another question about this.
Because this is it's interesting that a full solution of the Navier-Stokes equations can be a full reduced order model, but it is reduced order here because it's a macroscopic simulation of the mold filling, and we have absolutely no simulation of what really takes place during the solidification in between dendrites and whatever have we, and all that we didn't do. So what we actually thought was that, okay, could there be some system in, or some pattern in, which thermal fields that are actually detrimental for both segregation as well as, you could say, centerline porosity. And of course the centerline porosity, that was the Niyama criterion that takes cooling, T dot and gradient into account and all that. So we wanted to see whether we could do something simpler than what people did. I mean, Rapin and Danzig and you and so forth. I mean, you did this on the scale where it actually took place, you could say.
It was not at that time, but
later on. Yeah. But still, so what we wanted to do here was to say, okay, well, can we actually try and simulate this with a simpler model and still at least improve the process? So that was the idea. And that was the reason why we did not continue with that, because others were actually doing that better than us. And we should then, in the beginning, just reach their field or their level. But here we had the Magmasoft, which was this code that could simulate this on a more macroscopic level. And then what was interesting was also that during the optimization, and that was quite interesting, we did a simulation including the Navier-Stokes equations for validation. So we saw segregation as well as centerline porosities where it actually took place more or less. And then doing the optimization, we switched off the fluid flow simulation.
Yes, of course.
So we only did the thermal simulation. Yes. And that was interesting. So we did a number, I don't know how many hundred or whatever, 50 or 200, whatever, of thermal calculations. and then we found the optimal solution there. It went from 60 to 46 tons. And it was cast by Wittkowitz heavy machinery, a huge, humongously big a plant in Czech Republic, and then it showed no defects. That was really interesting. And then we took Magmasoft afterwards and did the fluid flow simulation again to check the one that was optimized only based on the thermal field, and we saw that we got a lot less centerline porosities and as well as segregation. So that was a kind of validation with the reduced order model, but not the totally reduced order model, but that was because that was the thermal model, right?
Yep.
Yep.
So that was absolutely necessary for optimization to proceed with this reduced order model.
Yes, because otherwise, I mean, think of modeling this with the macro, and yes, exactly, and then doing all these scenarios. We would have been, it would have taken 2 years in CPU time, right?
Okay, so now I think that we should take care about what we call a reduced order model.
Yes.
Because in the computational community, reduced order model, it has a specific meaning. It is when you have a complex computational model and you proceed to POD decomposition, proper orthogonal decomposition. It means that you keep the complexity of the model, but you, for instance, if you proceed with finite element, you change the interpolation basis in order to get a reduced stiffness matrix and to solve faster. But you didn't lose any complexity. What you call a reduced order model on your side is not exactly this.
No. It
is to use what I would say a simplified model.
For sure.
In which, for instance, the small scale physics is ignored and it is condensed in a simple criterion like Niyama.
Exactly. Yes.
So I think maybe it would be better to speak about a meta model.
Yes, but I entirely agree.
Because ROM reduced order model,
that's reserved for something which is more specifically defined. I entirely agree. Yes.
So, okay. Well, I think that was, yes, you explained. So finally, you explained that regarding modeling of casting processes, you didn't continue this work. Okay.
No, not so much. No.
Because if we talk about casting, the two other papers are on a very different topic.
Yes.
The gray iron.
Yeah.
Which is a really interesting material.
Yes.
Yeah. So it's I remember because I was a member of the committee of the thesis of Tito Andriolo.
Yes. Exactly.
It was a very original work.
Yes, it was for sure.
At least seen from my side.
Yes.
I was impressed by the contrast between what I knew from you before.
Yes.
Modeling the process at process scale.
Yes.
And then when I discovered the PhD of Tito, it was another scale.
Yes.
We were at the scale of the nucleus.
Yes.
And with quite original and impressive innovations.
Yes.
So that was very nice to see how you modeled the structure of the nucleus, of the nodules. I appreciate it very much. So
thank you very much.
I don't think if we come back, maybe I have a question because. You have shown in your slides today that first you overestimated, it was the thesis of Tito, in fact. The Young modulus, the prediction of Young modulus was overestimated.
That was with the unit cell approach.
With the unit cell approach.
Yes.
And afterwards, there were two things that improved the results, if I remember.
Yes.
To take into account peripheric surfacic region in the nodules.
Of the nodules, yes.
And also taking into account, as you said, the residual stress that occur during cooling.
Exactly.
Okay.
Exactly.
And that was really verified, let's say, and you have perfectly illustrated that when you passed the specimen into the synchrotron, and
Yes.
It was really a nice study. So, what was really the first order factor? It was to take into account the residual stress, or to take into account this peripheric region in the nodules?
Well, we saw from the slide there that I don't know whether I could go here. Let's see.
Because on the charts you have shown, we can see that the model is much better. So it is not. Yeah, it's this slide, but
yeah.
I think it's with residual stress.
Yes.
That we can. So it is still at the bottom right.
Yeah. So we have to the upper right we have the unit cell approach, and to the left we actually have the real cross section that was loaded and enmeshed in finite elements. So what we see here is that to the left, if we can do like this, does it? Is it appearing? No, okay. But particles are treated as voids to the left. That gives a huge deviation. Then isotropic particles with no residual stresses. Then isotropic particles with residual stresses. And then finally, anisotropic particles with residual stresses. And that's what gives the best agreement. And this is also what we can see down here, the red curve, both, especially at the curve to the right, the red curve with the triangles. That's anisotropic with RS with residual stresses. So it's a combination of the two, because when you assume that they are anisotropic, you actually calculate the residual stresses more realistically, so that when it's loaded, it reacts.
So the anisotropy coming from the structure in platelets of graphene.
Yes.
In each sector of a nodule.
Yes, exactly.
Okay.
Yes.
Okay, very good. Because I thought that on the top of that, the surface of the nodule, which is in contact with the matrix,
yes, but that's true.
had a specific structure, and that was also important to take that into account.
But that was taken into account as well.
Yes,
yes, that's true.
But it is less important than the other factors.
I think so,
Okay.
but we didn't evaluate them by isolating them. So I cannot tell whether it was the surface description or the fact that it was in conical sectors and platelets in combination with residual
I think
stresses.
that's also coherent due to the fact that we can see the mesh. But when we can see the mesh, the mesh, the finite element mesh, is not so fine to be able to describe reliably the surface region of the nodule.
No.
The mesh is not so fine. So probably this is consistent with what you said.
Yes. I think you're right. I mean, the mesh is.
Yeah.
The mesh is there, right?
Yeah. So the mesh is refined, but not so much in this periphery.
No. As you see, there are only 5 million elements.
Yeah.
Only 5 million. Yeah. And it actually calls for a lot more if we should do the resolution that you say. True?
I have a comment on those two papers, because we are all concerned about quantitative evaluation. And if I'm not wrong, the number of citations is not that much on those two papers, whereas they are excellent papers.
Yes.
What do you think of that?
Yeah, that's yeah. I don't really.
Because
it's difficult to say.
This material is a very popular material.
Yes.
So
I think
your contribution is really important in that field.
Yes.
And despite of this, the number of citations is low.
Yes, I think it's I don't know whether it's 20 or 30.
It's 20. Whereas your other papers, some of them are more than 200. So.
Yes.
It is strange, and I think we can think about it.
Yeah.
The number of citations.
Yes.
It's not correlated.
Always. No, not always, for sure. I entirely agree, and I would say that this was really novel work, But it might be that when you look at casting and modeling of casting, it's not as, you could say, as sexy or as much, you could say, focus when it comes to funding bodies, when it comes to being real science, when it comes to, I mean, and this is what casting has suffered from, this kind of old and dusty and kind of image, which is, of course, total nonsense when it comes to whether you do high-level science or not.
Exactly.
Yeah.
Exactly. Okay, thank you for that. Mm-hmm. Yes. All right, I think we can move to atomization.
Okay. Yes, thank you.
Atomization and spray forming. Mm-hmm. So, in fact, I realized that you classified your contributions in 6 topics, but there are 5, because atomization and especially spray forming is nothing but additive manufacturing. Spray forming.
Oh yeah. Okay. So what you're saying is that this is an additive manufacturing process.
Yeah, definitely.
Yes, you're right.
Definitely.
Right. Yes. But if I tell people that I do additive manufacturing, and then they say, okay, what are you doing? Yes, have a look here, and they would say, what the hell are you talking about? So that's why I haven't called it additive manufacturing. But you're right, it is an additive manufacturing process. Yes, that's true.
Especially if we compare the latest stages of development that you have shown for spray forming deposition, okay? And if we compare with DED simulation you have shown, it's exactly the same.
Yes, and I actually also, in my thesis, in that chapter, refer back to the 2 equations here.
You have
for the droplets.
Particles in flight interacting with an energy source.
Yes.
That's the same thing.
Exactly. That's true.
So that's nice to have this this picture here.
Yeah. So you're right. It is an additive manufacturing process. Yeah. But people wouldn't call it 3D printing.
Yeah. It's not
3D printing.
Yeah, definitely. Now we say 4D printing.
Yeah. Whatever. Yeah.
Okay. Yeah. I had. Yeah, so the innovation was, as you have explained, the fact that the interaction between the particles and the gas was more
that was taken into
developed than in former models.
Yeah. And even though this was a one-dimensional approximation of the spray cone, but it doesn't expand that much. So that was actually, you could say, kind of okay. And when we compared with experiments, it was relatively good.
So that's a point I didn't understand quite well, because you say, well, the atomization model, it's a 1D model.
Yeah.
Okay, because not so much expansion.
Exactly.
Okay, the angle is okay. Yeah. But when you come to deposition, you take anyway a second dimension, and it is the model of Mather.
Yes.
Because you have a m dot that depends on the radial coordinate then?
Exactly this one. So we made local, you could say, what we did was that we said, okay, well, we make, that was a one-dimensional model, yes, but then we took different grouplets, different droplets represented by different distributions, and they interacted with one another, and then they were deposited as a function of radius. So the larger particles in the middle, the smaller at the outside, meaning that we could emulate some radial effect.
Yes. So what we have, I don't know if I can use that. It doesn't work.
For some odd reason, it doesn't work.
Okay. So so you discretize your space radially.
Yes. That's
in
the deposition model.
Here.
Yeah. Only in the deposition model.
In the deposition.
Yes.
And on each block, k plus 1 and so on.
Yeah, sure.
There is one part of the Mather Gaussian m-dot distribution.
Yes, there is a local.
Okay.
Yes, exactly. Yes, yes, and that has different temperatures or different enthalpy because it is a local, you could say, a local distribution of droplets as a function of radius.
What I didn't understand is that there is no link between this Gaussian radial distribution due to Mather and your one-dimensional model. What is the link between the two?
The link is that we have, I mean, perhaps it's not that well described, but we have these. Here we look at single droplets and also distributions. But then we said, okay, well, we know that this distribution of droplets is different if we look at a distribution that is just below the atomization point that has a higher mean diameter than outside. Mm-hmm. So then what we did was we took this one-dimensional model and then we sent all these distributions through it. And then we assumed that some of the distributions at the center have a higher mean diameter than outside. So they were still interacting with one another in the one-dimensional mesh, but we had the effect of having smaller particles at the outside being more represented rather than at the inside. So that was a way of emulating a radial dependence. Mm-hmm. Yeah.
Okay. Right. Well, I had a question, of course, on the interactions between the particles, because you don't comment that much on that.
No, and of course there was no I mean, in these models here, the particles only see one another through the gas, you could say, thermally speaking. And then they are accelerated in the one-dimensional momentum equation we see here, which in essence is just Newton's second law with a drag term, and then that's it. For the simple ones.
It means that when you write, you say, well, to compute the evolution of the gas temperature, we will write a balance between the droplets and the gas. So in that field, the interaction between particles is also important, because if you have a density of particles that is non-uniform, then the interaction with the gas will be different. So,
but they are represented by distributions. So they interact with the gas. Yeah,
okay.
Yeah.
Sure, so maybe I didn't see that in the.
They are,
okay.
Of course.
Okay.
Yeah. But they don't mechanically, I mean, colliding and all that, no way. I mean, it's only they interact with the gas, different distributions, and affect the gas temperature along the way and their own temperature, and then we get these droplet temperatures during flight and blah, 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 and compare with experiments, and we can see that this was an improvement as compared to...
Whereas in reality, they can interact.
Oh, but of course. Yes.
Because when we are looking to powders issued from atomization, we can see some strong events of colliding.
Of course, and this
satellites and so on.
And this is what we tried to start looking into with this. But this was in 2009, I think, 15 years ago, and I will imagine that people today doing a modeling of spray forming, I don't know whether there are people that that are actually doing this also from a mechanical viewpoint with collision and so forth and so on. But this is for sure doable, I think. But still, again, if you want to look at the process, if you want to also try and describe the process more at the macro level, it's always a choice of looking at scales. So there could also be representative volume elements or whatever here that we will have some coupling between a local and a global scale.
I think there is an error in the manuscript, because at the beginning, at the beginning of this chapter on atomization, you speak about, you tell the droplet experience rapid solidification resulting in an amorphous, glassy microstructure. Amorphous. But afterwards you speak about recalescence, you speak about S-DAS.
Yeah.
So
Of course. Yeah.
Okay?
Yeah, that's
so
true.
I think this might be maybe corrected.
Yeah, true.
Okay. Yes. So then, what was interesting was how you superpose bricks and construct a model. You start from atomization and then deposition, sticking law.
Yeah.
So the sensitivity of the results to the sticking law is not so discussed in the papers. What do you think about that?
Well, I remember, as far as I remember, the sticking has two components, right? It has a geometrical component and it has a thermal, you could say, or a solid fraction component.
Yes.
Yeah. And I think that what we saw was that it was mainly the solid fraction component that was important. And I think that the sticking law that we have was simply just multiplying the two. I think it was a relatively simple one there. But no, we didn't look into trying to vary the different phenomena to see what was more important. What we did was that we, of course, compared with the building of especially Gaussian shapes, and then we got something that looked quite similar, and that was, from our kind of perspective, a reasonable, you could say, validation. But you're right, we could have gone more into the looking at the sticking law. But at the time, the novelty was also actually just on the coupling between the atomization and the deposition.
Absolutely.
So to us, that was actually novelty enough. But you're right, one could have discussed also the sticking efficiency, the SE, I remember.
Yeah, because when you have in hands a model like this, then it's very interesting to play with the model.
Yes, of course.
In order to see what is first order importance in the model.
Yeah.
And where to put some money in material characterization or characterization of the additive efficiency and so on. That's one of the major advantage with the development of numerical models, actually. Okay. Well, I was surprised also when you finally developed the open form model. You come back to compare with analytical models from the literature, and you don't come back to your previous models, in order to see what was really the added value of the development of the open form model. And I was a little bit frustrated because I thought very interesting to evaluate the potential of the simple models with the latest developed model.
I understand your point. I think the main answer to this is that we looked at this area, you could say, a calculation domain very close to the nozzles. So just predicting that flow, you see it's 200 millimeters, we don't have any deposition whatsoever. So that was why we didn't compare with the coupled atomization deposition model, because this was focusing very much on this particular flow. But what we did compare with was experimental findings as well as model findings by Markus and Fritzing and Udo Fritzing in the University of Bremen. We were collaborating very much with him, and he did very nice contributions to the field of modeling of this. And this was for sure you could say, an improvement to both our models and his models in predicting the mean diameter. So that was the main, you could say, metric we used for evaluation. But I think the main reason is that we looked at this particular part of the atomization process close to the nozzles.
I remember also on this process, I think maybe it was in a conference And the talk was given by Annie Anine from University of Alberta in Canada. And he showed that after deposition, because the metal is deposited as semi-solid,
Yes.
okay, so it's still semi-solid for a long time, and then there is a slight flow, creep flow, deformation of the material. So did you have you looked at
not at all.
at this?
No, we didn't do that.
Okay.
Yes. So these papers we did. This is the latest. That was in 2009. The first of the spray forming was in 1998. So trying to combine with a creeping flow of the deposited material and looking at that would have been killing us calculation-wise totally. But you're right, it would have been interesting to also couple it with that.
Well, one of the interesting points in these developments, it is the shading algorithm.
Yes. That was challenging.
You didn't insist that much on that, but it's a smart job.
Exactly. Yes. That took for some. We had to remember some geometry in 3D, and that was not so easy.
Yeah.
But I remember these papers. This I actually coded myself. Later on, it was, of course, PhD students, blah blah blah. But this was actually that took some time making that work. These models there. Yeah.
Definitely. Okay. Okay. Well, maybe we can move to tape casting. I don't know where we are regarding the time. Still 10 minutes. Aha. Okay, tape casting, just for, well, I think we all appreciate analytical equations.
Yes.
So it's really one or two papers, I don't remember exactly, but these are very nice papers.
Yes.
Developing differential equations.
Yes.
So I agree with the fact that, for sure in France, I don't know in Denmark, but the PhD students are less comfortable with differential calculation.
Yes. I think it's the same all over the place.
Yeah. But it's very nice what we can deduce from simple analysis. I was surprised because it is for slurries of ceramic materials,
yes.
Okay?
Yes.
And then you started with quasi-Newtonian. It is a non-Newtonian, but okay.
Yes.
And then you moved to Bingham.
Yeah.
But was it the same family of slurries? Because
these two material descriptions are.
Is there a real threshold?
I don't.
It was an exercise.
It was more an exercise.
Okay.
Yes.
Okay.
To show that it could be done for a Bingham fluid with 2 doctor blades, and of course, obviously, no one in literature did that at the point in time. So we found that interesting. But you're right; it's a question of whether that particular slurry that we used was. I mean, it was non-Newtonian, but not that much. It could also be described by a Bingham fluid.
Yeah. So very recently, when reading these papers, I concluded that I could transform them as an exam for PhD students for lectures I give in fluid mechanics and so on. So it's very nice, very nice. And
happy to inspire you on that.
And of course there are some typos in your publications.
Yeah.
That are replicated in the book.
Okay. Yes.
Okay. Well, we can move maybe to additive manufacturing then. The real additive manufacturing.
Yes, the real apart from the spray forming. Yes.
Okay, that's definitely a great series of papers. The meso, especially the meso model, because the macro model, I have the same kind of remark as Paulo, and maybe just to make a comment on that first, on those macro model to deduce residual stresses. we are facing a wall,
yes.
trying to discretize the laser path, and at the same time predict the residual stress in at the macro scale.
Yes.
It's a huge challenge.
It is a very huge challenge for sure. Yes.
Because what you did was very smart, but I think it's valid. We agree on that. It's valid on the very first layers, but no more, and not for a complex geometry. But
oh yeah, the one with the scanning strategy.
Yes.
I remember you wrote that it was only one layer, but I would say it was not one layer in the sense that the part that was optimized was, of course, many layers. So the part that did like this, and then when we did the island scanning based on the optimized scanning process, then it was, you could say, flat.
Because I understood that in the paper that was in the list, it was only one layer, and in another paper, you cite it in the book. It
was several layers, exactly.
It was several layers.
Yes.
Yeah. Okay, so that's for the macro modeling. And then I appreciated very much, of course, the mesoscale analysis. Yeah. So that's there again we can see a considerable improvement, development of a numerical simulation. That is quite impressive.
Yes.
To obtain, I think, one of the best simulations at the international level,
yes.
I can see.
Yeah.
So that's definitely a remarkable contribution.
Thank you very much.
So if we can come back to I have just a comment on the first paper, which was the beginning. I think it was at the beginning of the thesis of the Mohamed Bayat.
Oh, the first paper on
the conical source.
Yes.
Okay. Yeah. Yes, so here we are.
This one.
Here we are, yeah.
Yeah.
Like, here we are, okay. So, that was the justification of this conical shape laser source is, for me, it's quite surprising. And why? Is it because of the powder layer?
I mean, the one to the right there, that we suggested that?
Yes.
It was because that we had an expectation that the heat source was not constant throughout, like this top hat or this to the left.
Yeah.
So we wanted to.
You have in-depth absorption of the laser radiation.
Yes.
Okay.
Of course.
And the justification for that is the powder layer.
Yes.
Because of multi-reflection between the powder particles.
Yes.
Correct?
Yes.
But in fact, in the mesoscale simulation, at the very beginning of a track, you are in this situation that, of course, you have to melt the powder bed to initiate a track. Mm-hmm. But once this is done, when the laser advances, the laser radiation is on the melt pool. Is it not on the powder bed anymore?
No.
So,
yeah.
So why insisting on such a model, whereas we know that on the steady state regime, it is out of purpose, I think.
Yes.
Do you agree on that?
Yes, I could agree on that. It was more like fun, right? Trying to make.
I think it was also more like the beginning of the work.
Yes, but that's for sure where we
made the same errors.
Yeah.
And when you are not so familiar with a process, you learn from the process. And then true. You think, you say, that's the wrong way.
Yeah. That was. I would say that this was not much needed for sure.
Yes.
That would be fair to say.
Except if we would like to focus on defects that would occur at the initiation of a track.
Of course, yeah.
Then that would be relevant.
Yes.
Of course. Okay. Then we can see that as compared to the latest results you have shown, well, the surface is flat and
course,
so on. So there's a lot of.
So this was much. I mean, of course, this was much more advanced. Yeah.
Yes. Yes, what is surprising also, because when you speak about the boundary conditions you prescribe, you speak about Marangoni effect.
Yes.
Okay, which, so if you could come back on the slides before. Okay, so there is the flat surface.
Yeah, sure.
You have to prescribe tangential stress.
Yes.
And then you say, well, I need to prescribe this force in a certain thickness. I think that you tell this.
Yeah, I think we did it as a volume force, but a very thin. I think we did, but I don't exactly remember. Yeah.
Because
because it is a surface tension, of course.
It is a surface tension,
sure,
but
sure.
If the surface is discretized, it is the case here. It is the real surface of the mesh.
Oh yeah, but that's for sure.
Then you can implement directly a tangential stress.
Yes.
You don't need to implement it in volume.
No.
But I think after, when you work with Flow 3D, with VOF methodology,
then it's a surface tension.
Then you have to convert surface tension into a volume force.
Yes, and this is what you are discussing here, right?
Exactly.
Yeah.
Exactly. Okay.
Yeah. I think, I don't know whether, this was Flow 3D. Yes.
That's Flow 3D. Yeah. So the results are.
I think the other here was consult.
I had some questions on ray tracing.
Yeah.
Because you say, well, we proceeded to ray tracing. That ray tracing, it's not so obvious in such condition because the keyhole is not that stable.
No, you can definitely say that. It's very unstable. Yes.
So the ray tracing, of course, ray tracing is simple as compared to general ray tracing because the rays are oriented, and then we study the multiple reflections of each ray and so on. Do you proceed to this analysis at each time step, or is it because it is time consuming also?
Yes, I think.
Could you comment about time consumption for ray tracing and how many rays did you have in your discretization order of magnitude?
Yeah, this I simply don't know. I don't remember. But I think it's in every time step.
Every time step.
Yes,
So that
that
could be, but we have the chance that you have the chance that with maybe a limited, maybe 1,000, 10,000 rays.
Yes.
It's enough to simulate.
To simulate it, yeah.
The transfer of energy.
Yeah.
Okay, but okay. And yes, for those papers, they are highly cited. More than 250. Citations.
In a couple of years or 3.
Yes. Okay. Well, just a comment because we compared with you. Because benchmarking between computer codes is also quite useful. Validating with respect to analytical formulations, that's okay, but comparing between different computer codes is very, very useful, and we have learned a lot doing this. So we compared with your results, and there is still one point I didn't understand in your results, is that I find that the surface of the bead is too flat with respect to reality. So I don't know if you have an opinion about that. Where does it come from? Because it's obvious. Does it come from the implementation of surface tension? Or?
I would imagine that would be the main, you could say, explanation. But I haven't. I mean,
unless
yeah.
I think there is there is one point on that. So
yeah.
Maybe we could benchmark.
Yes, that would be nice. Yes, then we could actually initiate the collaboration that you were talking about that we haven't had before. Yeah, that would be one way of doing it. Yeah. But I'm happy that you compare with us.
Yeah. You remember I asked you the rights for one figure.
Yes.
You have shown it. That we implemented in one of our publications. Yes. Because we have the results of DTU and in parallel our results. Yes. So this was one citation more for you.
Yeah. Okay. Thank you so much. Yeah.
Okay. Yes. Yes, when I come to a multi-layer and to the DED simulation. So.
Yes.
Yes, both articles are also very impressive.
Yes.
So it is again Flow 3D, which is definitely a very nice computational tool.
That is really a nice tool. That's for sure. Yeah. Yes.
So we can see that it's very close to spray forming, and when we can see that. Yes. Do I have some relevant questions on that? Yeah. Well, maybe I have one question on gas. So the particles, they are carried by a gas.
Yes.
And the gas is not really treated in that.
No, I think it's just prescribed.
Yes.
Yes.
So I think there is do you think there is a real interest in considering a gas particle interaction? Because gas particle interaction has been taken into account in the spray model,
exactly,
but not in that model.
No, I think the gas velocity is just prescribed here.
Yes.
So we have particles, of course, at a certain size. There is a size distribution, and these are kind of flying in an enveloping gas, and that gas velocity is prescribed here. And this is, of course, the first what you would start with, because this is the simplest. But depending on whether the particle-gas interaction and the calculation of the gas as the Eulerian phase in a Eulerian Lagrangian formulation, as this would be, it's a question of whether this would be important or not. But at some point in time, definitely somebody will do it, of course, because it could turn out that that it will be more realistic than just prescribing the velocity, I'm pretty sure. But again, this was one of the first models of its kind in literature, so we had to do some assumptions in the beginning, and that was also, of course, assuming that the velocity was just prescribed. But yes, you're right, that is definitely one way where we could start improving the model, one area. But it will definitely increase the CPU time, beyond discussion. Yeah.
So what would you say to conclude on that topic, to develop a macro-meso dialogue?
Yes.
Is it something important for you, and what do you think should be done on that?
Yes. Then I can perhaps get something out of the extra slides that I actually did here. Where do we have those? Extra slides here. Do we see them there? Yes. And then, is it this one? Yeah, so I will have to, it's one of the last ones. I don't know whether I can, yeah, there were so many. Yep. So, I think it is actually, you could actually say this one to some extent, it's also in the thesis, right? But this one, because this actually addresses what you're asking. This is where the hell did I put my glasses? There. So, yeah, exactly. So this is kind of the future vision where we couple the mesoscale simulation, the microscale simulation, mapping pores, mapping grains, what have we, making RVEs, and then getting average mechanical properties that we insert in the part scale simulation. This is exactly kind of the vision that we need if we would like to do multiphysics, multi-scale models with transfer of fields, coupling them together. This is what I kind of envision that should be done. And of course, some people are already looking into this, but really making a unified model as such is something that is yet to be seen.
Yeah, it's very difficult to build a consistent platform in which the different models at different scales are able to exchange information.
Exactly.
And that's really a tough job.
Yes.
Well, we can wonder, is it still research really, or software engineering?
Yes, that's true.
That's maybe borderline with respect to research, but quite important
yes,
anyway.
But I would say also the research would probably also be where to pick those RVEs and how the size of them. That calls for an understanding of the physics behind it and what matters for the determination of the mechanical properties. That's for sure.
But anyway, for the metals that are difficult to treat additively, for metals that are difficult to weld, let's say, that's really extremely important to develop such a platform, such a global view. Because, well, it's very nice to get results on the layer 1, layer 2, layer 3. But what is of interest for the industry, for real application of difficult alloys, it's layer 500, 1000 and more, and in which the initial temperature is not room temperature.
Yes, that's true.
So we have to exchange a lot of information between macro scale and mesoscale. Yes. And at the same time, as you answered to Paulo, using the mesoscale, we can think about identifying meta model, for instance, with a Goldak source, in order to boost the computational efficiency.
Yes, that's true.
And probably to create, using the numerical models, to create databases on which we can apply machine learning and so on.
Exactly. As I had in one of my slides, using high-fidelity computer models to produce data on which we do machine learning.
Exactly.
Yes,
exactly.
That's true.
It is beginning to be applied in the literature.
Oh yeah,
already.
For sure.
So, okay. Well, I think we can conclude on that, Jesper.
Okay.
And once again, I was really impressed.
Thank you so much, Michel.
Your contribution.
Yes.
And I will follow your latest development.
Yes.
And if we could collaborate, that would be with pleasure. But anyway, thank you for what you have brought to the field.
Thank you very much.
Thank you so much.
Thank you.
So, I have not been notified of any questions ex auditorio, and that means that we are close to ending the formal part of this defense. And let me just say a little bit about what is going to happen now. I already mentioned that the committee will convene immediately after we leave the auditorium to compile their recommendation to the academic council on whether or not to award the Dr. Technicus degree. Now, if the recommendation is positive and unanimous, then the academic council decision is automatic. And in that case, Jesper will be awarded the degree at the annual commemoration party on May 2nd next year by our president. I would like to thank the committee, the two official opponents especially, for their hard work, first as making the assessment for the acceptance of the thesis for defense, and then preparing for this defense, and conducting the session that we have just witnessed. A big thank you to Jesper, of course, also on behalf of the university, and a thank to everybody in the auditorium for witnessing this procedure and witnessing that everything has gone on in the right way. Thank you very much. I now close the session and hope that you will join us outside for a small reception. Thank you very much.